Hi, I'm Peter Stern, venture partner at LDV and CEO of Voyant Photonics. So I'm thrilled to announce our next speaker. Anima Anandkumar is the Director of Machine Learning Research at NVIDIA and a Bren Professor at Caltech. Anima basically invented the use of tensor algorithms for machine learning. Tensor algorithms, as you may know, are central to effectively processing huge multidimensional data sets in machine learning and AI applications. At NVIDIA, she's leading the research group that develops next generation AI algorithms. And at Caltech, she's the co-director of the Dulcet program, co-leads the AI for Science initiative, and is the recipient of a named chair, which is the highest honor the university bestows on individual faculty. Anima, thank you for joining us today.
Thank you, Peter. And it's a pleasure to be here and great to see all the innovations that are going to be presented in this summit. What I want to briefly talk about today is the impact that deep learning and broadly AI has had over the past decade and how we can use it in many scientific domains and make a long-lasting impact for the benefit of humanity. One such arena is tackling climate change. This is the most important problem we are facing today. We have seen a dramatic increase in extreme weather events. Many of us have personally seen wildfires and orange skies. I have seen flooding in Hawaii when I was there last year. We've seen snowstorms in Texas. So I can keep talking about how this is having such a big impact on our lives and certainly what it bodes for our future generations. So what do we do about this? How can we tackle this? The most important thing for this, is our ability to predict climate change accurately. We need a crystal ball. We need to be able to accurately say what will happen a century from now. We do have climate scientists modeling and saying that there will be dramatic rise in sea level, for instance. But we also need more nuanced predictions for every region at a very fine resolution. And that is much harder to get. And for that, we need not just the current generation of supercomputers, we need big leaps in both computing power and our algorithms. For instance, in the 1990s, when the first generation of climate modeling came about, this was at the resolution of few hundred kilometers. That's the resolution at which they could predict the climate over the next several decades. But then this is not accurate enough, right? So we need to get to a much higher spatial resolution and be able to resolve the weather phenomena in a very fine scale manner to be able to get accurate climate projections. For instance, we are on the path to getting a 1 kilometer resolution in the next few years. And with that, we'll be able to resolve convection and remove some of the parametric assumptions we are making in the current climate modeling. But then we really need to be going to sub-kilometer resolution to get accurate climate projections. For instance, we need to be able to resolve storms and extreme weather events, and that requires 100 meters. And ultimately, to get to 1 meter resolution, we would be requiring about 100 billion times more computing power than what we have today. But that is the resolution we need in order to be able to resolve the stratocumulus, which are the low-lying clouds. And that is the biggest factor of uncertainty in climate modeling today. So we cannot get there by just making bigger supercomputers. Even with all the hardware enhancements and developments, we are not going to get there. And so what is the workaround? How do we get around this huge requirements in computing abilities? That's where we can ask what AI and machine learning can do in terms of achieving these scale-ups. can we get 1,000,000x or larger speedups with the use of machine learning? And we have to do that in a principled manner, because ultimately climate projections is about getting good uncertainty quantifications, right? This is about extrapolating to the future, which is not what current machine learning methods are very good at. So how do we get to this really hard challenge, and what are principled approaches we can embed into machine learning to make this possible? So this is where we recently announced our model called ForecastNet, which is a Fourier Neural Operator based AI model that can achieve the unprecedented spatial resolution compared to any other deep learning based model before. And unlike numerical weather projections that are currently made, which use physics-based calculations, ours is completely data-driven. So by training it on the past data of weather, we're able to accurately predict not just the average weather events, but also the extreme weather events. So what you saw here in this visualization is our ability to predict these atmospheric rivers, which are hugely important because those predict storms, those predict extreme weather events. They predict whether there will be a wildfire because we'll be having a drought. And so you can see here our ability to predict that accurately. And so the way we went about achieving this is developing this technique called Fourier Neural Operator that can achieve a fine resolution in predictions, even if it's not trained on that highest resolution data. So in essence, it can handle varying resolutions of inputs and still give you accurate answers. And so to me, this is a great first step in being able to use this model downstream in so many applications. And this is a foundation to our Earth-2 effort, which aims to create a full digital twin of this planet and use that for climate projections, for assessing vulnerability to human life. All these aspects require us to build this accurate digital twin. And here at NVIDIA, we have jump-started this effort with ForecastNet. We are looking towards building an unprecedented supercomputer to solve these hard challenges. And it's a pleasure for me to be here and tell you about that. Thank you.